This video is part 2 of a short series summarizing my notes for the aerodynamics, the design theory, stability, and testing of flying wings. If you haven't seen part 1, I have a much more detailed introduction there, and many of the topics in this video build upon the last, so give that a quick watch before this one. So to start things off, taking it all the way back to the basics, remember that for any aircraft to fly, there are two basic minimum requirements that must be met. Number one being the aircraft must fly in a static equilibrium, and that must be at a useful positive lift coefficient. And number two being the aircraft must have sufficient stability, which is the ability to maintain or to return to a specific flight condition after being disturbed.
Now, I know that many of you will consider the content of this video just as complicated math that doesn't really have anything to do with your project, but let me give you an example of why this is actually important to understand. And if you don't actually run through these exercises yourself, I think this video will still be a useful exercise for you to increase your understanding about how planes really fly. Let's very quickly consider how spins develop by only considering how the rolling moment changes when the aircraft is subjected to a roll rate. For a stable flight, you want your aircraft to be returning to equilibrium conditions when subjected to a disturbance in all three directional moments, the same thing applying to pitching, rolling, and yawing. If a gust of wind induces a yaw or roll of your aircraft, and your aircraft does not return to that equilibrium state after the disturbance, you are no longer in controlled flight. We want the aircraft to converge to equilibrium conditions with minimal oscillations. In the case of rolling, there's an important concept referred to as roll damping, which describes the change in the rolling moment due to the roll rate of the aircraft, and we'll dive into this more in depth later in this video. But if you think about it, as the wing rolls downwards around the fuselage, the local lift increases as we move outboards toward the wingtip, because out there the airfoil sees the incoming air at an increased effective angle of attack due to the wing movement. This is great because as the rate of rolling increases, the downturning wing will generate more and more lift in a direction against the roll, and the same roll rate counteractive effects will happen on the other upturning wing. Now, if we consider post-stall conditions on the same wings, since the lift curve slope turns negative here, the roll damping effect also flips signs, and this means that if any roll rate is introduced here in a post-stall condition, which generally happens because one wing stalls before the other, then the wings now generate lift in a manner that rolls the aircraft further into that same roll. And this is exactly how spins start, and this is why the content of this video is important for you to understand, even if you're not diving this far into your design. I've included these two tables of the definitions of the most common aerodynamic quantities, and I won't be slowing down to redefine these every time I mention them in this video. So if your understanding on all of these isn't complete, please just pause the video and take a screenshot of this so you can refer to the definitions as we move through the rest of the video. The analysis of aircraft stability and control is a fundamental result of rigid body dynamics. Rigid body motion consists of translations and rotations about the CG, and these can be described as 6 degrees of freedom: forward and aft motion, upwards and downwards motion, and lateral translations, as well as pitch, roll, and yaw. In a broad sense, stability is just the tendency of a system to return to its equilibrium condition after being disturbed from that point. There are two main types of stability or instability that are important. First of all, static stability, and second of all, dynamic stability. An airplane must have a stable system with acceptable time constants, meaning in general we want the dynamics to be acceptable, but actually more than just stable, we need appropriate damping and frequency here. Following the general motion equations, we have 3 equations for body forces, 3 equations for body moments, and 3 equations for kinematic pitch, roll, and yaw rates. These equations are nonlinear second-order differential equations and are a little bit difficult to evaluate. The second-order DFQs can be used in aircraft stability for pitch, roll, and yaw damping and stiffnesses, but I think that's beyond the scope of this video, so I might save that for another one. We can make assumptions, though, that if justified can linearize the equations and make stability analysis a bit simpler. To quickly review static stability from aerodynamic first principles, we can evaluate the aircraft motion by isolating the moments about each axis independently. Doing this yields lateral directional or roll-yaw stability and longitudinal stability, which is more critical and complex than lateral directional stability. If a wing is displaced from its equilibrium condition to a higher alpha, and therefore a higher CL if not near stall, it should return to a lower CL to be statically stable. Like we reviewed in part 1, this means that the pitching moment should be negative as CL increases. Again, this is just static margin, implying neutral stability for x equals 0. Typical static margin values range anywhere from 5 to 40%. And you might think, if we need the pitching coefficient of a plane negative, why not go all in and make it extremely negative and extremely stable? Well, as the pitching moment coefficient, if less than 0 can be thought of as the pitching stiffness, becomes increasingly negative, the aircraft will become more and more difficult to maneuver from steady flight. And if an aircraft is too stable, it'll be sluggish and difficult to handle. Again, this was covered in part 1, so see that video for a bit more of an in-depth discussion and derivation on this. Back to the basics, a force or moment can be represented as a function of 9 primary inputs, these being instantaneous linear velocity vectors, instantaneous rotational velocity vectors, instantaneous control surface deflections, and then all 9 of these also have their time-dependent counterparts, also referred to as rates, totaling 18 terms. These forces and moments are proportional to dynamic pressure and can be normalized using dynamic pressure for more useful forces and moments in aircraft analysis, and this represents a range of speed and air densities with one term that is normalized to dynamic pressure, so you can see how this is helpful in analysis. Dynamic pressure is one of the more important dimensionless parameters in aerodynamics, denoted by Q, which is just the 1/2 rho v squared term in the general aerodynamic force equation. It's also nice to, wherever we can, non-dimensionalize force and moment function terms for any analysis, and this can be done with wing platform area, chord length, span, or other custom aircraft parameters. We can also take the lateral velocities, W and V, and convert these into incidence, alpha, and side slip beta, and it's also not uncommon to non-dimensionalize the body rates P, Q, and R using 2 times the velocity over a reference length, where that reference length is chord or span as appropriate. You'll see this non-dimensionalization of the body rates in 3 or 4 slides from now. These equations of motion are sometimes used in a non-dimensional form where all the states and derivatives are non-dimensionalized, and this is particularly helpful when comparing aircraft to aircraft or condition to condition. So this information is cool and all, but can we really use it to describe how an aircraft flies? Because obviously this generalized form isn't super helpful for that. We can actually gain a ton of insight into the handling and performance characteristics of an aircraft through a proper stability analysis. And to do that, we can derive what are called stability derivatives. Stability derivatives are dimensionless or aero-normalized coefficients that quantify how an aircraft's aerodynamic forces and moments change in response to small variations in flight parameters, such as angle of attack, side slip angle, and angular velocities, for example, pitch, roll, and yaw rates. These derivatives are critical for predicting and analyzing the stability and dynamic behavior of an aircraft and enable proper control system design, ultimately ensuring safe, predictable, stable flight across various conditions. The quasi-steady forces and moments representing the rigid body, or aircraft if you like, 6 degrees of freedom, are laid out here. There's a bit of confusing nomenclature here where L is rolling moment rather than lift, N is yawing moment rather than normal force. Now, if we consider also the effect of control surface deflections in these functions, we can quickly explode into 18 dependencies for each degree of freedom, meaning that there will be 108 derivatives, including the new control derivatives, which is really unmanageable in any practical context. Instead, we can make some reasonable assumptions to simplify things. We sometimes can assume symmetric flight in the XY plane, which means that the asymmetric terms y, l, and n will go to 0. It also follows that the derivatives of these quantities and their derivatives with respect to u, w, q, and delta E, delta elevator, will also go to 0. If we're doing a symmetric stability analysis, this will eliminate 54 of those derivatives. The control rate derivatives, which are all the delta terms, are usually small enough to be considered negligible on a macro stability analysis, so we can cut a few there too. And through aircraft flight test studies, it's also been determined that the acceleration derivatives are normally not significant. With all of these, we're left with 18 critical stability derivatives, and using all these assumptions and non-dimensionalizations mentioned a minute ago, we now have a more useful form of the aerodynamics-driven 6 degree of freedom representation of an aircraft. The force and moment coefficients are functions of alpha, beta, PQR, and elevator, aileron, and rudder deflection angles. It's pretty nice to express the angular rates here in a non-dimensional form, like we mentioned earlier, and this is helpful to compare different aircraft. Now, just like the general equation of aerodynamic forces, there is an equivalent form for the aerodynamic moment produced. This follows basically the same form as the force equation, but notice that instead of a reference area, the moment form uses the product of the reference area and Mach, which is mean aerodynamic chord. These two coefficient forms are
a really important building block for further stability analysis, which we'll dive into right now. I'll explain this as quickly and basically as possible while still capturing the essence of this. We can express the force and moment equations in the last slide as a Taylor series expansion with respect to a reference flight state denoted by z sub j here. In the expansion, the partials are the stability derivatives, and it's my understanding that the terms associated with the double, triple, and higher derivatives here are sufficiently represented by the first order partials, and we can ignore those for the most part. Stability derivatives are essential for studying aircraft dynamics, but they aren't sufficient on their own. They must be associated with a defined reference condition that encompasses all the variables in the force and moment equations, and in most cases, the reference values are straightforward. For instance, the goal is to fly the aircraft without side slip, right? So the reference value for beta would be 0. Similarly, during straight and level flight, body rates are nearly 0, making the reference values for P, Q, and R also practically 0. And with equilibrium body rates set to 0, it's natural to assign 0 as the reference values for the rudder and aileron as well. The following breakdown of the major stability derivatives is in the body axis system, but later if I mention derivatives in terms of C sub L rather than C sub Z, just know that the transformation from the body axis system to the stability axis system simply involves rotations by the angle of attack and side slip angle. The stability axis system is defined to align with the relative flow, and it's basically synonymous with the wind axes. Realignment from the body axes to stability axes makes it easier for us to understand how aerodynamic forces like lift, drag, and side force act around an aircraft and how the aircraft responds to those. Considering a typical equation for the normal force z, the coefficient c sub z as a function of alpha primarily depends on the normal force generated by the wing, with small contributions here and there by the body and the undeflected tail, as most of the normal force is generated by the wing. If a wing uses a symmetric airfoil, the normal force should be proportional to alpha, but if there's any camber present, there will be an additional contribution to the normal force over the existing proportionality to alpha, and that depends on the camber line curvature. The important stability derivatives here are the camber effect CZ naught, CZ alpha, which is how the normal force changes with changes in alpha, CZQ, which is how the normal force changes with respect to the pitch rate, which is again majorly reliant on a tailplane, and CZ delta E, which is just the effect of elevator deflection. The pitching moment equation has a similar structure, and this is defined partially by the variation in the pitching moment coefficient with respect to the incidence of the aircraft with no control surface deflections. In general, the aircraft's CP will not be coinciding with the CG, and in most positively stable aircrafts is slightly behind the CG. This just means that the wing camber effect will, once again, provide an additional contribution past pure alpha proportionality to the wing's normal force, and as you can see here, this is reflected in the pitching moment equation as well. The last term is another elevator deflection contribution, and with this whole equation, you can algebraically derive the elevator term relationship to the other variables by just holding the pitch rate and net pitching moment to 0. The side force and rolling moment equations follow the same structure as the normal force and pitching moment equations. I won't go into too much detail about the side force stability derivatives, but I can summarize this by saying that a rudder and fin displaced from the yaw axis of the aircraft during a side slip causes local incidence and therefore side force, and a similar thing happens with the rolling moment since the CP of the fin is generally displaced from the roll axis. The side force stability derivatives include CY beta, which is how the side force changes with respect to side slip angle, CYP, which is how the side force changes with respect to the roll rate, CYR, which is how the side force changes with respect to the yaw rate, and two control derivatives, which are the rudder and aileron deflection contributions to the side force. Aerodynamic prediction codes can generate numbers for all 5 derivatives here, but the 3 most important are CL beta, CLP, and CL delta A. CL beta is sometimes referred to as one of the Dutch roll derivatives and is super important in determining lateral stability of the aircraft. However, this often depends on several more complicated geometric factors such as wing hedral angle and wing, fuselage, and fin geometry definitions. CLP is the rolling moment due to the instantaneous roll rate, and we'll cover this later. CLR is how the yaw rate affects the rolling moment, which can have a negative impact by amplifying Dutch roll if the stability derivative is negative, giving adverse rolling conditions. And the primary derivative here is CL delta A, which is the effect of deflecting the ailerons. And of course we have the rudder term, but this isn't easily handled for tailless aircraft as we don't have a traditional rudder, but instead mixed elevons.
The Yawing Moment equation is where things get difficult for tailless aircraft stability because the Yawing Moment derivatives depend greatly on a traditional tail fin. The first term, Cn beta, is determined primarily by the fin characteristics and sets the weathercock frequency in yaw, which can quantify the aircraft's tendency to turn into the wind after experiencing a side slip disturbance. We'll cover more of this and how it applies to tailless aircraft in a few minutes. CNP is the effect that the roll rate has on the yawing moment, and this is again dominated by vertical surfaces. The third term, CNR, is yaw damping, and this provides dynamic stability by damping yaw oscillations. The fourth term, CN delta R, is a huge player as the rudder is a primary control mechanism. There will still be some effective rudder deflection term, but it gets more complicated with elevons. There is also still a small effect of aileron deflections, generating differential drag in the wings during deflection. Again, more on all of these stability derivatives, as well as what they mean and what affects them in a few minutes. You may have picked up on the problem presented for an aircraft without any vertical surfaces, without any winglets, fences, or fins. How are we supposed to generate positive yawing and side force stability without these? Well, a careful combination of sweep, taper, aspect ratio, and more importantly, wing twist can push us just above that neutral stability criteria. Later in this video, you'll see how things change when adding winglets to a flying wing. In a future video, however, I would like to dive into a parametric study of this. For practical purposes, I'd like to show an example stability analysis, but to do that, we first need to understand what each of these stability derivatives means, what we should expect the value to be, and what affects these values. To start, the derivatives related to forward velocity are CXU, CMU, and CLU. CXU represents speed damping and is how the axial force, which is primarily drag, changes as the forward velocity changes. CXU should be negative as increased speed increases both parasitic and induced drag, and this is negative because the total axial force becomes more negative as velocity increases. CMU is how the pitching moment changes as the speed changes, and CLU is how the lift coefficient changes as the speed changes, and these are both dependent on compressibility effects, which is beyond the scope of this video, so I'll only include them here to say that when doing analyses assuming incompressibility, these will be zero. To understand how the pitching moment changes in the aircraft, we can look at the three stability derivatives CMQ, CM alpha, and CMU. CMQ is the pitch damping derivative and describes the changes in pitching moment due to the pitch rate. Clearly, this should be negative for convergence, providing a nose-down restoring moment that damps and opposes the pitch motion, and this is critical for dynamic longitudinal stability in modes of short period and phugoid. A horizontal tail is the major contributor to pitch damping, but without a tail, the wing sweep angle and wing CP location also have a little bit of an effect, so this is something to watch carefully in designing a tailless aircraft. CM alpha describes how the pitching moment changes with angle of attack, and this should be negative. Please review the last video for a complete derivation of this and to understand why this must be negative for a stable aircraft. CMU describes how the pitching moment changes with changes in forward speed, and just like CLU, it's dependent on compressibility effects, and for low speed, incompressible analyses is usually small and close to zero. To understand what affects the rolling moment on the aircraft, we can understand the three stability derivatives CLP, CL beta, and CLR. CLP is the derivative that is associated with roll damping, and a negative value here indicates positive damping, otherwise known as convergence. And this is expected because an aircraft's rolling motion will typically be damped by the opposite roll aerodynamic forces acting to resist that roll. This value will decrease with wing taper, and in post-stall regimes, since the lift curve slope flips to negative, the roll damping term will also flip to positive, and this is exactly where spins start. As a side note, which will be specifically helpful when looking at CNP in a few slides, when wings are subjected to a roll rate like this, it's clear that the sections of the wing towards the wingtips will be in augmented local flow conditions, as the wingtip moving upwards in straight flow experiences an artificially and locally increased incidence angle, thus increasing the lift generated in the section. This figure here shows that the lift distribution can be considered to be linearly increasing with buttline station. CL beta describes the rolling moment caused by a side slip angle, not yaw rate, side slip angle, and is called the dihedral effect, and is one of the most important parameters for lateral directional stability. The dihedral effect is where side slip results in a rolling moment that stabilizes the aircraft. When an aircraft yaws, one wing may generate more lift than the other, causing a roll in the opposite direction, and for stability, the aircraft should roll away from the side slip, not into the side slip. This means that CL beta should be a negative value. This is a common aerodynamic response called adverse roll and can occur in an aircraft without specific design elements like dihedral wings to counter this effect. CLR describes the rolling moment generated due to a yawing motion or rate and is usually negative in aircraft that have minimal dihedral in the wings. In adverse yaw, when the aircraft yaws, a rolling moment in the opposite direction occurs because of asymmetric drag between the wings. CLR is where, for aircraft with swept or dihedral wings, yaw-roll coupling can become problematic. A positive value is not uncommon though, and this just means that as the aircraft yaws, it experiences a slight tendency to roll into the direction of the yaw, which could be part of the natural coupling between yaw and roll dynamics. This is especially relevant in Dutch roll dynamics where yaw and roll are coupled and affect each other. Positive CLR helps with yaw-roll coordination and generally reduces Dutch roll oscillations by making the aircraft roll in the same direction as the yaw, leading to stability, and negative CLR, on the other hand, can lead to adverse roll, making the oscillations worse by causing a roll in the opposite direction of the yaw. The side force and yawing moment derivatives are really where the challenge of tailless aircraft is realized, as we must achieve the correct signs and values of these derivatives even without a tail. Aerodynamics does not care if you have a tail or not. If these derivatives are not proper, your aircraft will not be stable regardless of its shape or configuration. The three important stability derivatives in regards to yawing moment are CNR, CN beta, and CNP. CNR is the yaw damping term and describes a change in yawing moment due to the yaw rate, and therefore should be negative. This is practically the same as the roll damping term, but instead of considering the differential lift, we now consider the differential drag generated by the difference in dynamic pressure experienced by one wing moving forward and the other moving aft. CM beta describes a change in the yawing moment due to the side slip angle and should be positive. With a longitudinally displaced fin or vertical tail, a side slip will induce a restorative yawing moment to bring the nose back to the relative airflow. You can think of this one as a tendency to turn back into the wind, and this is the challenge for a tailless aircraft where you must make up this stability with a careful combination of wing twist, sweep, and taper. CNP is just like CLP, but this time is the change in yawing moment due to the roll rate and therefore should be negative. Looking at the same diagram, while the lift distribution is increased as we move down the length of the wing, we must remember that due to the local incidence increase, there will also be an associated increase in profile drag. This differential in profile drag will contribute to generating the yawing moment, and there will also be a similar contribution due to the induced drag vectors. CNP also plays an important role in coupling the yaw and roll during a Dutch roll. While CNP should be negative, this is not a strict rule for stability. A positive value here means that when rolling, the aircraft just yaws in the same direction, which is pro versus yaw. So to start on the side force derivatives, first we have CYR, which describes how the side force changes in response to the yaw rate, and this should be positive. Again, a vertical tail is the primary contribution to this derivative, but for a tailless aircraft, here's how we can approach this derivative. Even without a tail, we'd expect CYR to be positive because when the aircraft yaws to the right, the left wing moves faster through the air, experiencing an increased relative velocity and therefore more lift and drag compared to the right wing. This basically creates a net side force to the right, as the left wing generates more aerodynamic force than the right. So yawing right, which is positive R, results in a side force to the right because the left wing experiences more drag, pushing the aircraft in the direction of that yaw. CY beta describes how the side force changes in response to the side slip angle, and this should be negative to resist side slip. CY beta helps the aircraft weather vane, which ensures that after a side slip disturbance, the aircraft will naturally align itself with the airflow, and the vertical tail again is the major contributor to this derivative, and since the contribution goes to 0 for a tailless, finless flying wing, the aircraft must generate its stability through a combination of wing twist, taper, and sweep. CYP describes how the side force changes in response to the roll rate. This is typically really small or 0, but if anything should be negative, meaning that the aircraft will get pushed into the opposite direction of the roll. When the aircraft rolls to the right, the left wing rises and the right wing descends. The left wing, which is moving upwards, experiences reduced effective angle of attack and less lift, whereas the right wing experiences more lift as it descends. The result is a sine phi contribution to the net side force to the right, meaning that the side force is in the direction of the roll. If your level of involvement in your stability analysis is significant, then you should be watching all of your stability derivatives and, more importantly, understanding and validating them. But if your analysis is a bit less involved and you'd like just a quick rule of thumb for checking your design iterations, you can understand static stability by watching a few important coefficients. For longitudinal stability, CM alpha is the derivative you want to be looking out for. this should be negative, and if you have any questions on understanding that, go watch the last video. For lateral stability, CL beta is a derivative you should pay attention to, and this should be negative for stability. And for directional stability, CN beta is what you want to look out for, and this should be positive. Now, to get a bit more practical, I made a super quick 10-minute single iteration flying wing design with and without winglets, and ran them through a panel method VLM analysis. In this case, XFLR5, because I didn't have much time to get a proper AVL or semi-empirical model running. Now, let's take a look at the non-dimensional stability derivatives and see if their values agree with the definitions we just reviewed, which would then imply that the plane is stable. CXU is negative with and without winglets like we expect it to be. CX alpha is positive for both configurations, which is correct, and this is self-explanatory as CX alpha is the axial force change with respect to the angle of attack, and we already know that since axial force is closely related to drag, and that at high alphas the aircraft has a higher frontal area and generates greater parasitic and induced drag, the positive value indicates then that as alpha increases, drag increases and slows the plane down, which is stable. CXQ is positive for both configurations, and this is expected and indicates stability. During a nose up or positive pitch rate Q, the flow over the wings and fuselage sees an increased effective angle of attack, which leads to an increase in drag. Again, as the aircraft pitches up, drag increases due to both the change in airflow over the wings and the increased angle of attack experienced by the horizontal stabilizer. CLU is 0 as expected. CL alpha is positive for both configs, and this is expected because as alpha increases, the lift coefficient will increase, if not near stall. CLQ is positive for both configs, and this is expected. The change in angle of attack caused by pitching leads to an increase in lift during a positive pitch rate. This increase in lift directly translates to a positive CLQ, meaning that the faster the aircraft pitches up, the more lift is generated. CY beta was about 0 without winglets, and it turns significantly more negative with the addition of winglets. This makes sense if you think about it and indicates stability because with vertical surfaces displaced from the yawing axis of the aircraft, the fins generate more and more lift in the direction of the yaw rate, which is restorative and stable. CYP changed from 0 to a meaningful negative value with the addition of winglets. If you think about the nature of what CYP means from a couple of minutes ago, this makes sense. CYR changed from nearly 0 to a meaningful positive value, which again aligns with our definitions earlier for stability. CLP and CL beta are negative, and this is expected for stability. They were also indifferent to the addition of winglets, which also makes sense because these are rolling terms, not directional terms. CLR is positive in both configurations, and we learned earlier that this just means that the Dutch roll mode should be watched carefully. For reference, the Cessna 172 has a CLR of 0.096. The pitching moment terms are the same as the rolling moment terms CLP and CL beta, where the winglets made no meaningful difference to the pitching moment because, again, these are not directional terms. CMU is 0 as expected with an incompressible analysis. CM alpha is negative in both configs like we expect, and CMQ is also negative in both configurations like we expect it to be. Now here's where things get interesting. CN beta is positive and increased with the addition of winglets, which makes sense if you think about it because there are now two vertical surfaces reacting that yawing moment and properly damping any rate-induced oscillations back to a state of equilibrium. CNP flipped from a negative value to a positive one with the addition of winglets, and this couples yaw and roll where the aircraft yaws into the rolling direction, otherwise known as proverse yaw. With the winglets, the yaw roll coupling is enhanced and can reduce yaw damping if not an intentional design feature. I'm a bit suspicious about the change here. If I was to go back and make a third iteration of this, I think I would focus on understanding what happened here. CNR is nearly 0 and flips to negative with the addition of winglets. And like we just saw, the roll yaw coupling enhancement can cost the yaw damping and then flip the sign from near 0 positive to near 0 negative. It's clear that this quick design needs some careful adjustments to ensure that the directional stability and dynamic modes of Dutch roll and spiral are sufficiently damped, but that's exactly why I wanted to show you this list of raw stability derivatives to demonstrate what to look out for and what to think about when things change, and how to determine if the change is anticipated, unanticipated, and acceptable, or more importantly, unanticipated and unacceptable. I'm also fascinated by the intricacy of winglet design, so I plan on making a video on that down the road. To finish things off, now that we have a high-level understanding of stability derivatives and which are important for the aircraft in question, there are a few different ways we can estimate these and start quantifying our aircraft stability instead of just talking theory. Now, obviously, there are these textbook solutions like we touched here, but they often fall short with too much uncertainty due to the variance in the wing and aerodynamic body geometry from simple ideal shapes. Then there are semi-empirical methods. These model aerodynamics with a predictive approach that combines theoretical principles with empirical data. So using fundamental aerodynamic theories such as potential flow and boundary layer theory, a semi-empirical model can establish a basic kind of framework model incorporating empirical corrections and coefficients to account for complex real-world phenomena that are really difficult to model purely from first principles. Prediction codes like DATCOM that rely on experimental data and aerodynamic theory can be used only if a significant aerodynamic background is present in the user running the code. Then there are vortex lattice programs, or VLMs. This is a purely theoretical aerodynamic modeling technique based on potential flow theory, modeling lift distributions or circulation over a wing by discretizing the surface into a lattice of vortices and solving for the circulation distribution. These always assume inviscid and incompressible flow, and therefore cannot accurately predict boundary layer behavior. Since viscosity is ignored, this can't directly predict drag or separation or vortex shedding. It's mainly used for slender, high aspect ratio wings operating at low alphas and subsonic flow. A VLM is not a semi-empirical model because the traditional VLM relies entirely on theoretical calculations without incorporating empirical data to correct or adjust for real-world aerodynamic phenomena. So these results are only accurate within the limitations of the assumptions. Then there is AVL, which is Athena Vortex Lattice Program. This is a semi-empirical extension of the VLM, retaining the core theoretical approach for calculating lift distributions and induced drag, but now enhancing it with additional corrections like drag predictions and control surface deflections. Here, lifting surfaces are represented by many horseshoe vortices laid out in both spanwise and chordwise directions. This only requires the aircraft geometry and flight condition, and again cannot estimate drag. AVLs can also establish the stability derivatives for useful feedback early in the design process. AVL is a handy tool for bridging the gap between theoretical predictions and the real-world performance. Naturally, the next step to bridge the gap between theoretical analysis and real-world performance is a proper CFD analysis and aircraft study. I might make another high-level video outlining things like CFD turbulence models, flight envelope simulation, steady and unsteady analysis, and how to interpret the results, because there are hours and hours and hours of details to discuss on each of those. The last approach to verifying stability characteristics and estimating the derivatives and coefficients is low-speed wind tunnel tests. Before any professional aircraft flies, any analysis models and results must be verified. If there is a significant difference in results, especially in the stability characteristics of the aircraft, it's obvious why this would be a major issue when investing the time and the money into a maiden flight. To ensure that the aircraft experiences the expected static and dynamic stability characteristics and generates the expected forces and moments during all stages of flight with all control surfaces being used at one point or another, wind tunnel testing is crucial. A fixed sting mounting allows the static derivatives to be measured, and alternatively, a flexible joint mount would allow for dynamic derivatives to be measured, but a flexible mount can present significant structural challenges and is very rarely used in the tunnel. It's not uncommon, however, to estimate the dynamic derivatives using textbook approaches and validating in full CFD. I think that's about it for this video. I was really hoping to have gotten a few more flights in with my most recent wing iteration, but finishing up flight testing on an earlier wing and the combination of full-time engineering and school hasn't lent me the time to do so. This next wing iteration is fabricated, but has several small electronics and packaging issues that I need to solve before doing the first flight. So I hope that this video was somewhat helpful for you. I still need to cover dynamic stability modes, so that'll be covered in the next video. And then ultimately, I'm looking forward to showing how all these principles can be tied together into a stable, controllable aircraft design. Thanks for watching.